Hi guys, today we are going to be focusing on the left and right end behavior of the graphs of polynomial functions. So the cool thing, or the one characteristics about the graphs of polynomial functions is that regardless if we have a polynomial of even degree or odd degree or positive or negative leading coefficient, as x approaches positive infinity, the function value will either increase or decrease, as you can see. As x approaches negative infinity, the function value will increase or decrease, and that's what we're going to focus on, okay? So again, the ends will either go up or down, and the in-between action, like how many hills and valleys are we going to have, well, that's a different situation. So let's go ahead and look at the first case scenario. So case number 1. If we have a polynomial with even degree and a positive leading coefficient, what is the left and right end behavior? So I want to know, how do the ends behave? Are the both ends going up, both ends going down, one going up, one going down, and so forth? Okay, so now let's go ahead and break it down. If we have a polynomial of even degree, the ends is going to remind me of the square function. Okay, so the graph of the square function looks like this. Okay, what if the leading coefficient is negative? You know, turn that frown upside down. Oh, sorry, yeah, I said it wrong, but you get me. Okay, so if the leading coefficient is negative, then we're gonna reflect about the x-axis. So we're gonna look like this. Okay, so if we have a polynomial of even degree, the ends, not necessarily the in between. Okay, the ends is gonna remind me of the square function. We have a polynomial of even degree with positive leading coefficient. So what's the moral of this story? Both ends are gonna go up. Okay, so let's go ahead and look at the function value. So as x approaches positive infinity, the function is gonna be increasing according to our rough sketch right here. So that means that the function value is gonna go towards positive infinity. That's what we have right here. So as x approaches infinity, the function value is also approaching infinity, but for the y's. Okay, so like I'm gonna go like this. Okay, so as x approaches positive infinity, the graph is going up, so the function value is approaching infinity. Yeah, this is the worst graph ever. Sorry. Now, what about the left end behavior? How is the function behaving as we pull to the left? Okay, so as x approaches negative infinity with our fancy math notation, we notice that the function value, the graph is pointing up, so the function value is going towards positive infinity. Okay, so that's what we're gonna fill in the blanks. So remember, when we look at the x-axis, values to the right of the origin are positive, values to the left are negative. For the y-axis, values above the origin are positive, and values below the origin are negative. So I don't know if I hurt you or helped you more. Okay, so case 2, we're still going to look at a polynomial of even degree. Okay, so it's like, okay, we have a polynomial of even degree. Okay, even degree, then the ends are going to behave like the square function. Okay, so we have y equals x squared. Okay, so it reminds me of the square function. So again, if the leading coefficient is positive, that's the graph. If the leading coefficient is negative, that's the graph. Okay, cool. So in this case, we have a polynomial of even degree with a negative leading coefficient. So we want to describe with our math notation the left and right end behavior. How does the polynomial behave as we pull to the left? How does the polynomial behave as we pull to the right? So to facilitate this, let me go ahead and do the xy axis, and I'll do something like this. Okay, so as x approaches positive infinity, or as we pull to the right, we notice that the graph is pointing down. Okay, so that means that the function value is going towards negative infinity. Okay, now as x approaches negative infinity, so as we pull to the left, we notice that the graph is pointing down, so the function value is also approaching negative infinity. Okay, so the moral of the story is this: if we have a polynomial of even degree and positive leading coefficient, then both ends are gonna go up, so the function values at both ends are gonna go towards positive infinity. If we have a polynomial of even degree with negative leading coefficient, from a visual perspective, both ends point down. Using our math notation, the function values both approach negative infinity. Now, what if we have a polynomial of odd degree with a positive leading coefficient? Okay, so first of all, if we have a polynomial of odd degree, then the ends are gonna behave like the cubic function. Okay, so let me put both case scenarios when we have a positive and a negative leading coefficient. So I say the ends in terms of how many hills and valleys, that's a different situation, but the ends are gonna behave like the cubic functions. Okay, so it's either like this, and if we have a negative leading coefficient, we'll reflect, so this part comes down and the bottom part comes up. Okay, so the ends are gonna behave like this. Okay, so polynomial of odd degree, positive leading coefficient, this is how it's gonna go down. So let me go ahead and do my XY plane for a special effect, and then we are gonna go ahead write down the end behavior. So as x goes to the right, okay, but with math notation we'll say as x approaches infinity. Okay, as x goes to the right, what happens to the function value? So we're gonna say as x approaches infinity, the function value approaches what? So as we pull to the right, the graph points up. So that means that the function value is going towards positive infinity. Okay, so again in English, as we go to the right, the graph points up. Math notation, as x approaches infinity, the function value approaches infinity. Now we want to tell the reader, what does the end look like? So we just told the reader what the end looks like as we pull to the right. We want to tell the reader, what does the end look like? What does the left end behavior look like as we pull to the left? Okay, so as we pull to the left, then the graph is going down. But let's put that in with using our math notation. So as we go to the left, we're gonna write as x approaches negative infinity. What's going on with the graph? The graph is going down, so in this case the function value is going towards negative infinity. So we have p of x approaches negative infinity. Okay, fourth case scenario. So we have another polynomial of odd degree. So if we have a polynomial of odd degree, then the ends, again the ends, I don't know how many hills and valleys we're gonna have in between, but the ends is gonna behave like the cubic function. So let me go ahead remind myself of both case scenarios. And if you forget, you can just put this in your calculator. Okay, like graph y equals x cubed, bam, y equals negative x cubed, perfect. So fourth and final case scenario, if we have a polynomial of odd degree with the negative leading coefficient, what does the left and right end behavior look like? So how does the graph approach at the end, at the left side and at the right side? Okay, so in this case, this is what we're gonna have right here. Let me go ahead and do my XY plane. Yeah, cool. Yeah, that is terrible. Good thing I already passed this class. Fantastic. Okay, so we want to tell the reader what is the end behavior as we go to the right and what is the end behavior as we go to the left, hence the left and right end behavior. So as we go to the right, then the graph is pointing down, so the function value is going towards negative infinity. So let's put that. As we go to the right, or as x approaches infinity, the function value is going towards negative infinity. So cool. So we told the reader what the right end behavior is. Now we want to tell the reader what the left end behavior is. So let's do this. As we pull to the left, the graph goes up. So we can say it like that in English. Let's put it in mathematical notation. So as we pull to the left, or we're going to say as x approaches negative infinity, the graph goes up. So in this case, the function value is going towards positive infinity. Fantastic, cool. So we're gonna take out this information that we did, and then we are gonna graph a few polynomial functions without the use of a calculator. But before let's go ahead and knock out this fun problem. Okay. Okay, so let me move this. Okay, sorry, technical difficulties. Alright, cool. So it says a fun problem. Let p of x equals negative x cubed minus 14x squared minus 15x plus 5. And it says use arrow notation to state the left and right end behavior. So you can either graph this, or I think it'll be a little bit faster if we just take what we talked about right now. Okay, so lucky for me that not only do we have an odd degree, we have an odd degree, but it's actually a degree 3. So I don't really have to use my imagination. I know how the graph of the cubic function looks like, both with the positive and the negative leading coefficient. Okay, so we have a polynomial of odd degree with a negative leading coefficient. Okay, pretend you can read that. So if the leading coefficient was positive, then this is what we will have. But since the leading coefficient is negative, then this is what we're gonna have. Okay, so we reflect about the x-axis. So this part comes down and this part goes up. Cool. So pretend that's a really nice sketch. So we want to use the arrow notation to state the left and right hand behavior. Okay, so we want to tell the reader as we go to the right, what happens to the function value. As we go to the left, what happens to the function value. So in this case, as we go to the right, or as x approaches positive infinity, the graph points down, so the function value will approach negative infinity. So let's go ahead and write that out. So as x approaches infinity, the graph goes down, so the function value approaches negative infinity. Okay, so that's the first one. Okay, yeah, I didn't have a lot of space. Now we want to tell the reader what does the end behavior look like as we pull to the left. Okay, on the left side. So as x goes to the left, the graph points up, so the function value goes towards positive infinity. So let's put that with our arrow notation. As we pull to the left, or as x approaches negative infinity, what's going on with the function value? The function value is going up. Okay, so in this case, the function value is increasing. So we didn't really need a calculator for this, but if you want to punch it into your calculator, no one will ever know. Cool. All right. Now, what is the degree of p of x? So the degree is code for the biggest exponent on any of the variable terms. The biggest exponent is 3. So the degree of the polynomial is 3. Okay, write that wherever you have space. Maximum number of x-intercepts. Okay, if the degree is 3, then we're expected to have at most 3 zeros. If they're real number zeros, then we're expected to have at most 3 x-intercepts. That doesn't mean that we are going to have 3 x-intercepts, because if some of our zeros are non-real, then we're not going to have all 3 x-intercepts. Maximum number of turning points. Okay, so in English, turning points are like those hills and valleys. Okay, this is not the graph for this, but it's easier for me to do this one and that one. Okay, so in this case, if we had the graph of the cubic function, you know, we have 2 high and low points, so one high point or one low point. Okay, straight definition of a turning point. The turning point is a point where the graph changes from increasing to decreasing and vice versa. So in this case, the reason why this high point is a turning point is because when we were looking at this from left to right, the function value was increasing, and then we switched it to decreasing. So turning point. At this point, this low point, why is it a turning point? Because we were decreasing, and at this point we changed to increasing. But like in English, the turning point is like all those high and low points. Okay, so the question is, how many what's the maximum number of turning points? So it would have been nice if I read this segment for you, but I got a little bit excited. Now the maximum number of turning points. So if the degree is n, where am I? Okay, for this polynomial, the degree is n. The maximum number of turning points, or highs and lows, should be 1 less than the degree. So 1 less than the degree, we're going to take n and then subtract 1 from it. So this is why we has at most n minus 1 turning points. So check it out. Let's go ahead and look at our function. The degree is 3. What's the maximum number of turning points? Well, it should be 1 less than the degree. So in this case, it's 2. Okay. Zeros. What are the zeros to 1 decimal place? Are we supposed to do these by hand? Of course not. Okay, so let's go ahead and use our calculator. Okay, so we have a sense what the graph should look like. Okay, we should see the left end behavior. As we pull to the right, the graph should go down. As we pull to the left, the graph should point up. Hopefully we see that in the standard viewing window, and if not, then we'll fix it. Okay, so give me a sec. Okay, let me go ahead and graph the polynomial function. Oh, this is a dirty screen. Okay, I think you can see it without the glare. Okay, so the polynomial function, where was I? Okay, so we have negative x cubed minus 14x squared minus 15x plus 5. Okay, so let's go ahead and graph it. Okay, so we had said that as x approaches positive infinity, the function value should approach negative infinity. Did I type it incorrectly? Yeah, okay, cool. So as we pull to the right, I can see that the function value is decreasing. Okay, that's good. Now let's see if we can see the left end behavior. We see the right. As x approaches infinity, as we go to the right, the function value should be decreasing or go towards negative infinity. And that's what we have. The problem is that I don't see the left end behavior that we projected. We had said as x approaches negative infinity. So as we pull to the left, we have said that the function value should be approaching positive infinity. But on our screen, we it's going down. Okay, so you will play with the window however you can. There's no right or wrong way. Something that I like to do is instead of fidgeting with the numbers, I'm gonna go ahead do zoom out. So we're gonna hit the zoom button, which is the middle button, and then we're gonna do zoom out. Again, this is not like the best way or the worst way. This is just a quick way for me to do it without manually adjusting the window. I want you to notice where the cursor is right now, and it's blinking. So the calculator is going to zoom out wherever I have the cursor. So I'm going to zoom it out from there. So we can see the right end behavior. You know, it was going down. We weren't able to see the left end behavior. So now, looking at our prediction, we had said that as we pull to the left, function value should go towards infinity. What do we have? As we go to the left, function value should go towards infinity. So I think we got a good graph, but this right here that's like too close. It's a little bit not really nice for my eyes, so I'm gonna adjust the windows. I'm gonna hit the side arrows and trace it to whatever this value is, because we have to find the zeros. I'm gonna pay attention to the x value. Okay, x value is negative 12, so I'm gonna adjust the window so I don't have too much white space here. I'll adjust it to negative 15. Okay, so let's go hit window, and then x minimum negative 15, and then I'm gonna go ahead graph, and then if needed I'll adjust it on the right side. Cool. Yeah, so notice how this space right here is like too close to comfort, so I don't really like it. Okay, why? One of our problems is to find the local extrema, so we want to find the local max, local min. I can point to the local max, but the thing is, when it's so close, it's really hard for me to put the cursor to the left and to the right. So let me go ahead, just use my side arrows to see where I'm at. Okay, so right now the x value is at 1, so we don't need this much white space. Okay, so I'm gonna change it to whatever we want. Now I'll just change it to 5 or 10 depending on the mood that I'm in. Okay, I'll just change it to 10, kind of like from the standard viewing window. Okay, so let's look at this. So our prediction, as x approaches infinity, function value should approach negative infinity. So in English, as we go to the right, function value should go down. Okay, cool. As x approaches negative infinity, function value should approach positive infinity. So in English, as we pull to the left, function value should go up. Cool. So this is what I need for now. Okay, to find the zeros. Okay, so the degree is 3, so we're expected to have at most 3 zeros or 3 x-intercepts. We can see 1, 2, 3 x-intercepts. So for right now, let's go ahead, take this graph, find the zeros, and then we'll adjust it to see those highs and lows. Okay, so if you want the calculator to do anything for you, you gotta tell it by going by pressing second calc. Okay, cool. So we have second, and then we have calc. Okay, which is the trace button, and then we want to find the zeros. Okay, so let's go look at the zeros. it doesn't really matter which one you find first. I'm just in the habit of finding the zeros from left to right. That's how I maintain. I make sure I don't skip any. Okay. Where am I? Okay, cool. Okay, so the 0 is right here. We want to put the cursor anywhere to the left. So right now I'm somewhere on the right side. So let me go put the cursor somewhere on the left. We'll hit enter. And then it says right bound. So the 0 is right here. We want to put the cursor anywhere to the right. Okay, how right or how left? You know what? That's really a personal choice. Okay, guess. You could guess right there, or you can move it. Whatever. I guess I'll stay right there. And to 1 decimal place, the 0 is given by negative 12.8, I believe. Okay, so the zeros are negative 12.8. And let's go ahead and find the next two. So same thing, second calc 0, second calc 0. So the reason why the x-intercepts are called zeros is because at this point the function value is 0. Okay. So I think this is somewhere between negative 1 and negative 2. And right now the cursor is at negative 9. Okay, so I should just... Okay, that's kind of annoying. Give me a sec. Alright, cool. So it says left bound. So we are somewhere to the left of the 0. So let's go ahead and hit enter. Right bound. The 0 is right here, and you want to put your cursor somewhere to the right of it. Okay. Okay, I think we're good. Enter. We hit guess. I'll move it closer. I think that's pretty good. And then the 0 is about negative 1.5 to 1 decimal place. Fantastic. So again, the degree is 3, so we're expected to have 3 zeros or 3 x-intercepts. So 2 down, 1 more to go. Second calc 0. Second, where am I? Second calc 0. So let's go ahead, put the cursor somewhere to the left. I think we're good. Enter. Somewhere to the right. Enter. Guess. You can leave it there, or you can put it close to the actual x-intercept. And to 1 decimal place, that's about 0.3. Cool. So the zeros to 1 decimal place, thanks to your hard work, is negative 12.8, negative 1.5, and 0.3. Cool. All right. So now the local extrema, so the local max, local min. So bear in mind, this refers to function values. Okay, so let me go ahead and write it out. This refers to function values. Okay, the popular mistake is that students will write the actual ordered pair, but we want the function values. Maybe I should put local max value, but I don't do that because books don't do that. Okay, so let's go ahead, look at our graph. So we should have a dip right here. We could see the high point, but we should have a dip right here. Let's go ahead, adjust our screen. We want a lower y value, and you have two options. You can hit the trace button and actually trace your polynomial. You pay attention to the function value. So notice that right now, although you can't see it, the function value is negative 43, and you can keep doing that and see when you start to come up, and it's not a bad way, but sometimes it can get really tedious. Okay, I think we already started coming up. Oh no, I lied. Okay, but this can get tedious really quick. So what I like to do is I rather look at the table of values. So let's go do second table, and again I'm more concerned with the function value is to the left. So second table. Yeah, that didn't work. Second table. Looks like I already did this problem. Sorry. Okay, so I'm gonna look at the function values. So I know they're gonna be decreasing because it's gonna be something like this. Okay, so our end behavior, something like this. Okay, and then the hills and valleys are a little bit more prominent. Okay, so we should have a dip over here. I'm looking at the function values, and I think we started dipping at negative 265, so I'll just give it a little extra buffer. I'll make it to negative 300. Okay, so let's go ahead and adjust the window, and I want to go a little bit lower, so we'll do negative 300, and then we'll hit graph, and then let's see if we can see it. So I think that's pretty good. If you want to make it higher on the y side, that's fine. But check it out. We have everything that we need, okay? We still have the left and right hand behavior. As we pull to the right, function value goes down. As we pull to the left, function value goes up. The degree is 3, so we're expected to have at most one less turning point. So 3 minus 1 is 2, so we're expected to have 2 turning points, or 2 highs and lows. Okay, so we got 1 turning point, 2 turning points. So we did it. Let me just make this, let me take a screenshot. Okay, so let me go ahead and put my point here. Okay, so I'm gonna go ahead find the local max or local min. It's up to you which one you find first. I'll find you know what, if I go in order from left to right, I'll find the local min first. So second, calc minimum. So left bound. So the local the minimum point is right here, so you want to put your cursor anywhere to the left of it. Okay, once we have it to the left, then we'll put enter. Cool. And then right bound, put the cursor anywhere to the right. I think we're good. Guess you could be like I do, just put enter, or I'm trying to be a good person, so I'll put it closer to where that low point is. And although we just need the function value, my screenshot, I'm gonna put both the x and y. So the x to 1 decimal place is about negative 8.8. And the y to 1 decimal place is about negative 265.7. Cool. Let me go ahead and find that high point. So this will give us the maximum value. Okay, so second calc maximum. Second calc maximum. So again, pause and rewind as many times. So left bound, we're gonna put our cursor somewhere to the left, enter, somewhere to the right, enter. Guess, you can leave it right there, or again, I'm trying to be a good model, so I move the cursor close to where I think that high point is, and to 1 decimal point, that's about negative 0.6, comma 9.2. So hopefully I did this right. Okay, so my calculator is in the way, so let me look at the screenshot that we took. Okay, so the local extrema, so we want to know what is the local max. So we want to know what is the local maximum value. Okay, so maximum value, we look at function value. So in this case, the local maximum value is given by 9.2. What is the local min? Okay, the local minimum value is like we're looking at the low function value. Okay, so in this case it's given by negative 265.7. Fantastic. Cool. But again, we cannot well, that's the end of this problem. I just got excited. We cannot end this video right here. We talked about left and right hand behavior. I want to put our skills to the test. Okay, so let's go ahead apply what we talked about to actually sketching these polynomials. So let me go ahead, take out my paper. All right. Okay, so we're gonna do 4 problems because we're cool like that. But no, the real reason is because I want to do a problem illustrating each of the 4 case scenarios. We want to look at the case where the degree is even, odd, and positive and negative leading coefficient. Okay, so our to do is use the left and right hand behavior to sketch polynomial functions. So sketch is the key. Okay, so in this case, if we put our graphs on tops of each other, it's highly unlikely that they're not gonna overlap. But where they will consider is the zeros. Okay, so it says sketch the graph of a polynomial with even degree, negative leading coefficient, and zeros, negative 3, 0, 1, and 4. Cool. So you are gonna handle this however you like. Bear in mind that they don't give you the actual polynomial, so we cannot just cheat off our calculator. We have to actually apply what we talked about. Okay. If we have a polynomial of even degree, so it could be degree 2, 4, 6, 8. Cool. If the polynomial is even degree, the end is gonna remind me of the square function. I'm gonna put both case scenarios when the leading coefficient is positive and the leading coefficient is negative. If the leading coefficient is positive, the graph of the square function, looks like this. So both ends go up. If the leading coefficient is negative, we reflect about the x-axis and both ends go down. Okay, so in this case, we have a polynomial with even degree and negative leading coefficient. So what's going to be so special about our sketch? Both ends are going to go down. How many highs and lows are we going to have in between? Well, that just depends on what the on how many zeros that we have. So we are going to go ahead, just take the x-axis in this space. What about the y-axis? The y-axis is in my way. And then we're going to locate these zeros, and we're not going to graph them to scale. Okay, we're just going to put them about evenly spaced. So -3, 0, 1, and 4. Okay, if I took it in the actual graph paper, of course, there will be more space between these numbers. So the polynomial has these zeros. Okay, so these will be the x-intercepts. So let's go ahead graph those x-intercepts. Okay. We have established that the left and right end behavior is that both ends go down. In order for both ends to go down, as we graph this from left to right, we have to start coming up. So let's go ahead and start coming up. Okay, how steep? It just depends. How high or how low should my hills and valleys be? Well, that just depends at what angle you started. You know, if you started what should he say? Very steep, then your peak is gonna be kind of low. If you started I said it backwards, you know. If you came in very steep, then your peak is gonna be pretty high. If you didn't come in so steep, then your peak is gonna be kind of low. So hopefully I conveyed what I'm trying to say. Okay, so again, both ends should be going down. So in this case, when we do the graph from left to right, we should start coming up. And then we're just gonna go up and down, going through those zeros. Okay, so we go up, and then we have to come back down to get to 0, and we're gonna do our best to do a smooth curve. So again, how high or how low should my hills and valleys be? That's just dictated on how you started doing it. Okay, we put arrows at both ends, and we're gonna transpose this to the graph area. Okay, so this is like our scratch area. So let's go ahead and locate these zeros. -3, 0, 1, and 4. Okay, and then let's copy our results. We're gonna start going up and then go up and down till we hit all our zeros. Okay, so yeah, so let's go ahead, go up, down, up, down. So again, your highs and lows may be a little bit more prominent or a little bit more flatter, and it's okay. It's just, this looks like a line. Sorry, I try to make it look like a curve. Looks like I did a better job here. It happens. Okay, cool. So that's the end of that. Now, on a Quizzer test, you have to show this. That's a personal choice, but for me, it's just faster to write down my thought process here. Okay, all right. Fun problem 2 says sketch the graph of a polynomial with even degree, positive leading coefficient, and those same zeros. Okay, so pretty much it's the same problem. I just changed the leading coefficient, so I'm not gonna write everything. Okay, so we have even degree and positive leading coefficient, so the ends are gonna behave like the square function. Okay, so the graph of the square function is a parabola, both ends going up. So in our graph, both ends are going up, and the polynomial has these zeros, or these x-intercepts of -3, 0, 1, and 4. Let's go ahead, graph them. So we have already established that the left and right end behavior, both sides should go up. In order for that to happen, as we do this graph from left to right, we need to start going down. So we're just gonna go down. And again, how prominent should your highs and lows be? That's gonna be dictated on how you started doing the graph. You know, like when you're driving, like if you take a sharp curve or whatever. Yeah, you understood me. Okay, so the zeros are -3, 0, 1, and 4. Let's go ahead, start driving down until we go through all those zeros. Okay, so down, up, down, up. This was pretty nice, and then I got nervous and I did something sharp, but that's attributed to human error. Okay, so the graphs of polynomial functions should be smooth, continuous with no sharp curves. But we're human, so sometimes things happen. Okay, so we looked at both case scenarios for even degree, positive leading coefficient. We're gonna look at same both case scenarios, positive and negative leading coefficient, but in this case, the polynomial will be of odd degree. Okay, I got you. So it says sketch the graph of a polynomial. Sketch the graph of a polynomial with odd degree, positive leading coefficient, and zeros you can read. Okay, so if we have a polynomial of odd degree, the ends, okay, now I don't know about the in between action, but the ends is gonna behave like the cubic function. Okay, so it's gonna be something like this. So one side will go up, one side go down. If we have a negative leading coefficient, we're gonna reflect this about the x-axis, so this comes down and the bottom part comes up. Cool. All right, so in this case, we have a polynomial with odd degree, positive leading coefficient. Okay, so the moral of the story is this: the left and right hand behavior, as we pull to the right, function should go up. As we pull to the left, function should go down. These are the zeros: -7, 1, and 11 halves. 11 halves is 5.5 or 5.5. Okay, so let's do this. Let's go ahead, take the x-axis only. This is our thinking area, and the zeros are -7, 1, and 5.5. Okay, so if these are the zeros, they are going to be the x-intercepts. So let's go ahead and do our points. X-intercept at -7, 1, and 5.5. So we know what the end behavior looks like. You know, as we go to the left, we should be coming down. As we pull to the right, we should be going up. But the only way that this is going to happen is if when we do the graph, as we do it from left to right, we need to start going up. Okay, so what we're going to do, we're going to start going up and then go up and down until we go through all those zeros. Okay, so let's start driving. Oh, I tried my best. Oh, look, fixed. Cool. All right, so now does the end behavior hold true to what we said? Yeah, look, as we go to the left, we're coming down. As we go to the right, we're coming up. So let's go ahead, get our full credit. So the zeros are at -7, at 1, and at 5.5. Cool. All right, let's start to drive. So we're gonna start coming up. My hand is in the way, and then we're gonna go down, and then I missed it. Okay, I tried my best, but you have a pencil. Okay, I'm not gonna start this video again, but pretend I drove through 5.5. Yeah, I can't come back from this. Okay, but you get it, right? Cool. All right, let's go ahead and wrap this up with our fourth and final case scenario. So it says sketch the graph of a polynomial with odd degree, negative leading coefficient, and the same zeros. So again, we changed the earlier problem. So if we have an odd degree and negative leading coefficient, the ends is gonna behave like this. Okay, so the ends is gonna behave like the graph of y equals excuse me, -x cubed. So something like this. Okay, so the left and right hand behavior, as we pull to the right, the graph should point down. As we pull to the left, the graph should point up. Okay, so let's go ahead, take the x-axis and then graph those zeros. So -7, 1, and we had said that 11 halves is just code for 5.5 or 5.5. If these are the zeros of the polynomial, then they should be the x-intercepts. Okay. In order for the graph to go up as we pull to the left, then when we start to graph it from left to right, we need to start coming down. So let's go ahead, start driving down. We'll go up and down until we hit all our zeros, and then that's it. Okay, so we're gonna do our best to do a smooth curve without any sharp points. Oh, look at that, how beautiful. I wish I could submit this for credit, but I can't because graph paper is provided. So let's go ahead and locate our zeros. So -7, 1, and 5.5. So -7, 1, and then 5.5, and let the driving begin. Okay, so I'm gonna go down and then try to come back up, kind of like halfway between these 2 points. Okay, cool. And then I'm gonna go up and try to come down somewhere like halfway between these 2 points. I mean it's not like an exact measure. I just try to eyeball it. And if I had said that for my first problem, then I wouldn't have had this situation where I overshot it. Okay, but yeah, that's pretty much, that's what I should have said from the first problem. You know, go ahead, start driving, and then you start coming up or down, or turn it when you get to like halfway between them. So I think this one was my best work. See, it's true what they say, practice makes perfect. Thanks guys, we're out.